Hello everyone, welcome back. Today we are starting chapter 5, Introduction to Box-Jenkins Models. In this chapter, we will learn about a powerful approach to the modeling and forecasting time series data using autoregressive, moving average, and the combination of autoregressive and moving average models. That means the ARIMA model. We will explore the steps involved in the building of Box-Jenkins models, including model identification, parameter estimation, and diagnostic checking. Let us dive in and understand how these models help us analyze and predict time-dependent data more accurately. This outline what you should be able to do by the end of this chapter. First, understand why we use the Box-Jenkins methodology. It is a structured approach for forecasting time series, not just formulas. Next, ARIMA models, autoregressive model, integration for stationarity, and the moving average model. Then the four-step Box-Jenkins process: identification, estimation, diagnosis checking, and the last one, forecasting. Think of it as a roadmap for building and validating your model. Finally, autocorrelation function and partial autocorrelation function plotters help identify which components to include in the model. By the end, you will know both the concepts and how to apply them to real-world data. Time series probability models, called stochastic process, are essentially random events that change over time. For example, include daily stock price, monthly sales, or temperature readings. Many real-world time series are non-stationary, which means that average or variability changes over time. Because of this, we cannot directly apply simple models. That means patterns are not considering that's consistent enough. In Box-Jenkins model, many real-world time series are non-stationary, which means their average or variability changes over time. Because of this, we cannot directly apply simple models. In Box-Jenkins model, we often use differencing, calculating the changes from one observation to the next to make the series stationary. Stationary means statistical properties like mean and variance remain constant over time. Once the series is stationary, the Box-Jenkins approach allows us to understand the underlying process and forecast future values more accurately, which is why it is so useful for real-world data analysis. Here, we see the Box-Jenkins approach, which is one of the most widely used methods for analyzing. It involves three main steps. The first one, we identify an appropriate ARIMA model. This means looking at the data, checking patterns, and deciding which combination of autoregressive, integrated, and the moving average component fits the best. Second, we fit the model to observed data, estimating parameter, so the model accurately reflects the series. Third, we use the fitter model for forecasting, which allows us to predict the future values based on the historical data. The Box-Jenkins approach is popular because of it is very flexible. It works with stationary or non-stationary series, and it can handle data with or without seasonal patterns. Finally, this approach is supported by well-documented computer program, making it practical and easier to implement in the real-world situations. So essentially, this method not only models the data, but also gives us a reliable way to forecast and make informed decisions. Now, let us look at the concept of a stationary time series. A time series is considered stationary when it is statistical properties like mean and the variance do not change over time. This means there is no systematic change in the mean, so the series does not show a trend. There is no systematic change in the variance, so the data does not become more or less spread out over time. Any periodic or seasonal variation have been removed, so the series is stable. Different parts of the series show similar statistical behavior, making the data predictable. Strictly speaking, stationarity is a property of the model, not just the data itself. This is important because of the most Box-Jenkins modeling techniques assume the series is stationary before we start building of a model. Understanding whether a series is stationary is the first step in analyzing time series and ensures our forecasts are reliable. Now, let us focus on the ARIMA models, which are the most general class of models used for forecasting time series data. ARIMA are especially useful because they can handle series that needs to be stationarized through transformation like differencing or logging. And these models, lags of the difference series, are called autoregressive terms, which relates the current value to the past values. Lags of the error are called moving average, which account for the past shocks or deviations. A series that needs to be differentiated to become stationary is considering integrated model, meaning it is a differentiated version of a stationary series. An unseasonal ARIMA model is classified as ARIMA-PDQ. This structure allows ARIMA models to combine past values, differencing, and the past error into a single model, making them very flexible and powerful for forecasting complex time series. Operationally, a series is stationary if the mean, the variance, and autocovariance at lag k do not depend on the time. The term stationary time series is commonly used when the data appear suitable for stationary model. Many theoretical results in the time series analysis depend on the assumption stationarity. Therefore, non-stationary series are often transformed into stationary ones before the analysis. Operationally, a series is stationary if the mean, the variance, and the autocovariance at lag k do not depend on the time. That we call it stationary. Now, let us focus on the ARIMA models, which are the most general class of the models used for forecasting time series data. Now, let us focus on ARIMA models, which are the most general class of the models used for forecasting time series data. ARIMA models are especially useful because they can handle series that needs to be stationarized through transformations like differencing or logging. And these models, lags of the difference series, are called autoregressive terms, which relate current values to past values. Lags of the errors are called moving average, which accounts for the past shocks or deviations. A series that needs to be differentiated to become stationary is considered integrated, meaning it is a differentiated version of a stationary series. An unseasonal ARIMA model is classified as an ARIMA PDQ model. P stands for the number of autoregressive terms or the order of autoregressive model. D is the number of non-seasonal differencing passes, and Q is the number of moving average terms or lagged error in the equation. That means the order of the moving average. Now let us talk about the ARIMA models, starting with the autoregressive model. Suppose ET is a white noise process with mean 0 and the variance is sigma square error. A time series YT is an autoregressive process of the order of P. Autoregressive order P, the model is YT is equal to mean plus phi 1, YT minus 1 plus phi 2, YT minus 2 up to the phi P, YT minus P plus error term. This means YT as the observation. In autoregressive model, the current value of the process is expressed as a finite linear aggregates of previous values of the process and its shock. That means YT is that's the previous value and YT minus 2 is the previous year and up to the previous year of YT minus P. In autoregressive model, the current value of the process is expressed as a finite linear regression aggregates of previous values of the process and its shocks. Mean is, this one is the symbol of the mean. We call it that mu, as a parameter that determines the level of the process. When it comes to the second value or the second model, moving average model. Suppose ET is purely random process with the mean is 0 and the variance is sigma square error. Then a process YT is said to be a moving average process of the order of moving average order Q. Moving average model, YT is equal to mu plus the current time of the shock minus theta 1 ET minus 1 minus theta 2 ET minus 2 up to theta Q at the last of the time. This one is the previous shock and this one is also the previous shock. When you come to the model of autoregressive moving average model, that we call it ARIMA, the processes are processes that are performed as combination of autoregressive and the moving average process. Thus we call it ARIMA process of the order of PQ. P stands for the autoregressive and Q stands for the moving average. When you combine this one, autoregressive moving average model, here up to this one is we call it autoregressive. This one is autoregressive. And this one is the moving average part, moving average of order of Q. This one is autoregressive, the order of P. So we call it this one is autoregressive moving average model. Let us look at a practical example of an ARIMA model. A model described as ARIMA 0, 1, 2. That means it has 0 autoregressive parameters, so the past values of the series do not directly affect the current value. That's we call it as autoregressive, the order P. P is that's 0. This one is 0. And it has 2 moving average parameters which capture the influence of the last 2 errors or shocks. And the series was differenced once to make that stationary before fitting of the model. To identify the appropriate ARIMA model, For a time series, the Box-Jenkins methodology recommends a structured approach. The first step is to determine if the series is stationary. If it is not stationary, we take as many differences as needed to transform the original series into stationary one. This ensures that the model can reliably capture patterns and provide accurate forecasts. Now let us discuss differencing and the backward shift operator, which are key tools in the ARIMA modeling. Differencing is procedure that converts a time series of length n into another series, typically of the length of n minus d, to remove trend and achieve stationary. A convenient way to express differencing and lagged values through the backward shift operator B, by definition of BYT is equal to YT minus 1. That's, we call it that the backward shift operator, that's the power of 1. When you generalize this one, if there is the power of that's J, YT, we call it as YT minus J. So this one is the general form of the backward shift operator. When you come to the backward difference operator, the symbol of this one may be defined as the backward difference operator of YT is equal to the same as YT minus 1. That means the current time of the observation minus the previous observation, with corresponding of that's the time. YT minus 1 is equal to YT minus of YT minus 1, that's equal to YT minus, this YT minus 1 is the same as BYT is equal to YT minus 1. This one is the backward shift operator. So we can say it's YT minus of 1. This the same as the backward difference is equal to 1 minus of the backward shift operator B. So YT minus of YT minus 1 is the same as YT into 1 minus of the backward shift operator of B, because of YT minus of BYT is the same as this one. So YT as a common 1 minus of B. B means this one is the same as the backward difference operator. So we can write this one. The other one is when the power is increased to backward differencing operator, YT is equal to 1 minus of B square. YT is equal to the same as this one. Why this is important? Using the backward operator and difference operators provides a compact algebraic way to represent lags and differences. This makes building and manipulating ARIMA models much more straightforward, and especially when working with the multiple lags and the differencing steps. Today, we discussed the essential of the Box-Jenkins modeling. We covered the Box-Jenkins approach, an iterative method for identifying, fitting, and forecasting of the ARIMA models. We learned about the stationary ARIMA models, differencing, and the backward shift operator. That concludes this part of the chapter 5. We will continue with the next section of this chapter in the following session. Thank you, and see you in the next part of the chapter 5. Thank you.